Hi again. When we talk about energy transfer in space, we're talking about moving energy and light through space, and we're also moving um, elements as well, because the sun produces energy and light and elements that range from hydrogen to iron. In fact, we've got a lot of information coming at us from the sun. And when we talk about moving that information and transferring that, we talk about convection and radiation as two mechanisms for transfer. If you need an analogy for that, you can look at convection as kind of passing information to your classmates by moving in close to talk to them. So you're passing the information from your mouth to their ears through air. And when you talk about radiation, an analogy is sending that information via a text. So it's electromagnetic pulse to get it over to your friends. So if that helps you out with an analogy, let's go for that. When we talk about convection, we can talk about transferring that energy through a liquid or through a gas like air, and it's an organized flow to transfer that energy. This happens, and convection happens in space, really from the core of the sun out to the corona. That is a convective transfer of energy through the plasma of the gases of the sun. And when we think about convection and that movement, we can think about blowing on a hot bowl of soup so it's not too hot for us. So we're blowing and we're moving energy off of the soup. And you might say that convection energy must happen very quickly in the sun. But it's incredible that a photon that is produced in hydrogen fusion in the core of the sun takes hundreds of thousands of years to get out from the core of the sun to the corona. And that is due to the gravity force of the sun and of its mass, and also the relatively weak transfer of energy by convection. If we think about convection, we like to think about lava lamps. And I hope that you've seen a lava lamp before, because that is a way that you can think about moving photons from the core right down by the base of the lava lamp where the heat source is, out to the corona up at the top. The warm lava rises. Why does it rise? It's because it's getting heated at the bottom by its light source. And as it gets heated, the energy in those lava blobs starts to push out those lava blobs and make them bigger so that their volume increases. And when the volume increases in a diameter, like density equals mass over volume, it means that the quotient of the density is going to decrease. And when density decreases, this becomes more buoyant and less dense. So the lava can rise. But once it rises to the corona, those photons are out in the vacuum of space. And convection doesn't work in a vacuum. Radiation does work in a vacuum, and therefore it's the most important energy transfer process that we know. We're going to concentrate on absorption and emission as some of the processes that are involved in transferring energy by radiation. We've already talked about emissions, for the sun emits most of its wavelengths in visible light. The sun emits in all wavelengths, from gamma rays straight through to radio waves. And it emits more invisible light. But that's a beautiful thing, because the Earth absorbs more invisible light. And our eyes have evolved to act as a spectrometer also, and pick up those different wavelengths as color. When we talk about absorbing on Earth and absorbing visible light, you should know that the Earth and its atmosphere act as a perfect absorber. The Earth and its atmosphere can absorb all wavelengths. The atmosphere protects us by absorbing gamma rays and X-rays and UV rays. The Earth's soil can absorb visible rays. The ionosphere can absorb radio waves. So the Earth and its atmosphere tend to be able to pick up all kinds of radiation that hit it. Kind of like a pizza crust can absorb everything you throw on it when you throw on the works. All right? It can take in all forms of energy. And at the same time, the Earth can emit all of the energy that it takes in. And in fact, that is the sign of a perfect emitter. Think of this pizza crust and think of it as you sucking all the ingredients back into the refrigerator. This is sucking the oregano off. Whatever you threw on the pizza dust, at the end of the day, you can suck right off. And the Earth is constantly perfectly absorbing and perfectly emitting as well. It does emit all different kinds of radiation, but it emits more of the radiation in the infrared than in the visible wavelengths. We can talk about that a little bit more. A black body, like the Earth, absorbs perfectly whatever hits it and emits perfectly, but that doesn't mean that it emits exactly the same type of wavelengths. In fact, the emission is based on the temperature that all of that absorption causes. And the Earth doesn't get as hot as everything that hits it, so it can only emit in a lower wavelength. Let's explain it a little bit better. A black body is kind of the Earth is like a black body, and a black asphalt road is probably your best way to describe what a black body is that you know about. You know that a black asphalt road gets hot as blazes during the afternoon. You could not possibly walk on that black asphalt. It would burn the bottoms of your feet. The black asphalt absorbs all of the wavelengths that hit it, all of the invisible wavelengths, all the infrared wavelengths that come through the atmosphere and hit it are absorbed by that black asphalt. It gets very hot. At the same time, it is also emitting off some of those infrared waves. The Earth in general can't emit off as high frequency as it gets. It gets in a lot of visual. It can't emit off as hot as it gets. It emits off in lower wavelengths, in infrared wavelengths. You can even see some of that emission right here in the glow and in the mirage that is produced from that black asphalt road. The real emission happens overnight. When the sun is gone, this will continue to emit. Over the course of a day, an asphalt road acts as a perfect black body by emitting out very nearly what it gets in. At dawn, if you step on this road with bare feet, you're very happy. It's very nice and cool. In fact, it is cooler than the sand right next to it, which has a higher specific heat, and it will hold that temperature more. So this is an example that you know of a black body, and a black body doesn't necessarily need to be black, but it doesn't hurt. It just needs to absorb the maximum amount that hits it and emits out light waves as well. The light waves the emission light waves are based on the temperature that the absorption caused. There are laws associated with this that are important and that we need to know so that we can understand how the glowing stars around us emit out energy and how we can understand what they are emitting out. Are they emitting out gamma? Are they emitting out X-ray? Are they emitting out visual or infrared? These laws of radiation will help us to understand that a little bit better. The first law is Planck's law, and it's the fact that everything emits at all times. And everything means everything. The sun radiates, the earth radiates, the cloud radiates, the soil radiates, your desk radiates, you radiate. Every second of every day, everything radiates. That's why the black asphalt road can emit so well at night, because everything radiates. That's Planck's law. Law number 2, there's 3 laws of radiation. The hotter the object is, the shorter the wavelength that it emits. Look at the sun. The sun is so tremendously hot, and it puts out very short gamma rays, which are really hard to find anywhere else in the universe. It also sends out some lower energy UV waves. But the Earth can take in the visual waves and take in the IR waves, but the Earth does not get nearly that warm. And in fact, the Earth emits off the cooler infrared waves. That's called Wien's law. The hotter the object, the shorter the wavelength. That's actually an inverse proportion if you had temperature equals 1 over the wavelength. The hotter the object, the hotter the temperature, the shorter the wavelength. And you can note in here, the types of radiation emitted. The sun can emit in gamma, X-ray, UV, infrared, microwaves, radio waves, visual. The Earth does not have that kind of heat to emit off all of those different kinds of waves. So the Earth emits off in infrared waves that reflect the temperature that it has produced from its absorption. People radiate infrared waves. That's why you hear about, and animals too, that's why you hear about a 3-dog night, because the dogs can sleep all around you and radiate their heat off and keep you warm and keep you from freezing if you happen to be camping. That's what a 3-dog night is. It's also a really great band from the 60s. Law number 3. As an object's temperature increases, or as the hotter the temperature of the object, the greater its total energy emissions. All right? So the hotter the object is, the higher total of wavelengths that it emits. So, for instance, the sun emits about 150,000 times more energy per area than the Earth, because it's so much hotter than the Earth. And we can look at that as total wavelengths emitted. That is Stefan Boltzmann's law, and it applies to how we look at the relative temperature of stars. And when we look at relative temperature of stars, we're actually looking at their age. So we look at the total emissions that are coming at us from the stars in order to age them, as well as to find out their status. So those 3 laws. First of all, let's go over a few of them again. Law number 1, all things emit radiation at all times. And law number 2, the higher the object's temperature, the shorter that the wavelengths emitted. And number 3, as the temperature of the object increases, the total radiation emitted increases. Think about your oven on 200 degrees. There's a lot more heat coming out of it at 450. As the temperature increases, the total amount of radiation emitted increases. That oven emission, of course, is going to be infrared IR emissions. And I wanted to go over again with you. Law 1 is Planck's law. Law 2 is Wien's law. And law 3 is Stefan Boltzmann's law. Look over the text here so you get a good feel for it. These laws will come into play for spectroscopy, and that is next.